Okay, so here goes the first of many videos I'm going to be making. Just to let you know, this is happening in my basement, and currently the dryer is running, so if you hear any beeping, it's just the dryer, because we do wash our clothes in our house. The topic that we're going to be talking about for the next week or so is related rates, and really related rates is most related to implicit differentiation. So although we're coming out of 4.2 and 4.3 where we're doing curve sketching and then talking about position, velocity, and acceleration, now we're doing a different application of derivatives, and that is with implicit differentiation. So, as it says here, many relationships are dependent on one or more variables. For instance, water draining out of a conical tank is related to the volume V, the radius r, and the height h of that cone. All of these variables are a function of time t. So I've given you a nice artist rendition of a cone over here. Yes, that's what that is. It's a cone. And as you can see, my cone has some water in it. That's the blue. There's water dripping out of the cone. And at any given time t, there is some height associated with the water and some radius that the water will make with the cone. And as the water drops out, the height and the radius are clearly going to change, as will the volume of the water in the cone. So all of these things are related to a variable t, which is very interesting. So the first thing we need to talk about is just a known equation that we know that relates these variables, and that is the volume of a cone. And just so that you don't freak out, you don't have to know every volume surface area equation for this entire chapter. You'll see a lot, but often they're given to you. So if you don't remember, the volume of a cone is 1/3 pi r squared h. That is how you find the volume of a cone. And what we're going to be doing now is an implicit differentiation, and we are going to differentiate with respect to time, because as time goes by, things are going to change in our scenario. The rates of change are going to change, hence related rates. So we are actually going to take the derivative d dt, the derivative with respect to time t, of our volume equation 1/3 pi r squared h. So we're going to take the derivative of everything. If we take the derivative of a t, d dt of t is 1, but d dt of anything else requires us to use the chain rule. So let me break this down first, that we're going to take d dt of the left-hand side and then d dt of the right-hand side, to 1/3 pi r squared h. And the other thing you should notice is the right-hand side is going to have a product rule in it because it does have that r squared times h, so I can't forget about that. So on the left-hand side, the derivative with respect to time of v is just dv dt. And on the right-hand side, the 1/3 pi, remember, is just a constant. So I'm going to pull the pi over 3 out, and we are going to take d dt of r squared h. So I'm just going to do that over here, d dt of r squared h. And we know that that is a product rule, so we're first going to take the derivative of r squared, which is 2r dr dt, times h, and then take the derivative of h, which would be dh dt, times r squared. Looking at that, I have a dr dt and a dh dt. I have a derivative of the radius with respect to time and a derivative of the height with respect to time. But I also have an r in common, so I can say that this is r times 2h dr dt plus r dh dt. So if I pull that over here, I have pi over 3 times r times 2h dr dt, that's an r, plus r dh dt. And we see that that is how the change in volume with respect to time is related to both the change in radius with respect to time and the change in height with respect to time. This right here, dv dt equaling the right-hand side, is what we call a related rates equation. It tells you how the rates of change are related for the volume, the radius, and the height. So as you are looking through problems and you're asked to generate a related rates equation, you're simply asked to take the derivative with respect to what you're doing, and most often it's going to be with respect to time, our independent variable, and write it as the implicit derivative of the function that relates those variables. To actually do a problem out, they're not really difficult to do, and obviously the ones we start with are the nice easy ones. So for example 1, we're going to suppose that x and y are both differentiable functions of t, meaning that when you take the derivative with respect to t, it's defined. And they are related by the equation y equals x squared plus 3. So your paper should have an x squared on it. Mine, for some reason, doesn't like squaring things. The question is, can we find dy dt when x equals 1, given that dx dt equals 2 when x equals 1? So find the rate of change of y with respect to time when x is equal to 1, knowing that x is changing at a rate of 2 at that same time when x equals 1. So very simply, all I want to do is take the derivative, so take d dt of y equals x squared plus 3, and try to solve for dy dt when x is equal to 1. So taking the derivative implicitly, we get dy dt is equal to 2x dx dt, and then the derivative of a constant is still just going to be 0, so the derivative of 3 with respect to time is 0. I want to find dy dt when I'm given some information. I know that dx dt is equal to 2, and I know that x is equal to 1. Well, that's going to allow me to substitute into my equation and say that, okay, dy dt is equal to 2 times x equaling 1 times a rate of change of 2. So I find that dy dt is equal to 4, meaning that as x is increasing by 2, y is increasing by 4 at this time t, at any time t. So basically the y values are growing twice as fast as the x values for this particular function. Alright, so time for you to pause the video in a second and try this one on your own. So I'm giving you the information that x and y are both differentiable functions of t, and I want you to find the values that I'm asking you to find. In this particular example, you're given an explicit relationship between x and y, that y is equal to 2 times x squared minus 3x. And I would like you to find dy dt, knowing that x equals 3 and that dx dt is equal to 2. So go ahead and pause the video, do the workout. While you're gone, I'm going to do the work right here, and then we'll check answers. Okay, how'd you do? As you can see here, ultimately what we're looking at is, did you get a dy dt value of 12? You can do this in numerous ways. I decided to distribute the 2 inside and give myself a 2x squared minus 6x. And then I kind of get the dx dt twice when I take the derivative. And then substituting in my x value of 3 and my dx dt values of 2, I get 24 minus 12, or just 12. So that is how y is changing as x is changing at a rate of 2 when x is equal to 3. So let's try another one. Let's go on to the next page and take a look at what we have there. Alright, so what you might notice about example number 3 that's slightly different than the ones that we've just talked about is that the relationship here is not given explicitly. This is given implicitly, that x squared plus y squared equals 25. You may recognize that as the equation of a circle centered at 0, 0 with a radius of 5. So you can almost imagine a point moving around that particular circle, and we're going to look specifically at when x is equal to 4, what the value of dx dt is, and I'm going to give you another point that y is equal to 3 at this time, and knowing that dy dt is equal to negative 2. So why don't you give this one a shot and see if you can find dx dt under the given conditions for this function. Alright, and here you go. I got that dx dt is equal to 3/2. And I think one of the big things that I've been trying to show you guys throughout the year is, it's one thing to algebraically understand what's going on, but, what's going on in the function and why does this make sense? So, again, circle centered at 0, 0, radius 5. You have a point on your circle over here at 4, 3. And you know that y is decreasing because dy dt is -2. So we're actually decreasing the y value as x is getting bigger, which with dy dt being -2, you would know that as you move down your circle, the x value has to get bigger, so dx dt would have to be a positive value. So if you made a sign mistake in any of the transformations from the left side to the right side, just keep in mind that that has to be true. As that point is moving down in the y direction, it has to be moving out in the x direction to stay on the circle. So that's your first lesson in related rates, just kind of looking at functions. We'll get into a procedure and looking at some word problems as we go, but there are a few problems in your book that I've asked you to try that are just functionally based, just to get a handle on making sure you understand the process and you knock the rust off of your implicit differentiation skills. All right, successful video number 1, and the dryer did not even buzz. All right, guys, I'll talk to you later. Bye.